Okay, yeah, so here in this, we are going to discuss about traveling salesman problem using branch and bound. Already we have solved traveling salesman problem using dynamic programming. I hope you remember that how we did traveling salesman problem using dynamic programming. Now we are going to solve the same problem using branch and bound. So, like, what is the problem in traveling salesman? For example, if a traveler is let us take a small example. Let us consider like this. For example, if we have the nodes 1, 2, 3, and 4. Uh, so these are the different places we have. If a traveling person is starting from the node 1, he have to visit all the other rest of the node, and also it should be visited only one time, and finally he have to come back to the starting location. For example, if he is starting the travel from the node number 1, he have to reach 2, 4, 3, and finally he have to reach the node 1, and the rest of the node should be visited one. And one more condition is, and this should be done in minimum cost. So that is the problem we have in traveling salesman. So generally, we know in branch and bound, we will be solving this by making our state space tree. For example, if I am making a state space tree for this, how will I make it? First, the person is starting from the node number 1, or which means from the place 1. And then from 1, where are the other places he can visit? He can go to node number 2, 3, and finally he can also go to 4. And for example, and from 2, if he is coming to 1 and then to 2, and what are the other places he can go? From 2 he can either go to 3, or he can go to 4. And from here he came to 1 and 3. So what are the other nodes he want to visit? So 2 and 4. So now here in this place, he visited 1 and 4. So what are the other two places we will be having is 2 and then 3. Then if you see in this path, the person started from 1, he came to 2, and he came to 3. What is the only place left out is he have to visit the node number 4. And in this path, 1 is there, 2 is there, 4 is there, and the left out node is 3. And similarly, here the left out node is 4, here it is 2, here it is 3, and here it is 2. So this is the state space tree for this particular graph. So generally, as what I said, he have to travel, start from a particular node, have to visit all the rest of the node only one time, and with minimum cost. So generally, what we will be doing, we will be finding the cost for all the path. So what is the cost of traveling in this path, and what is the cost of traveling in this path? Similarly, this, and this, right? And then finding in all this, we will be saying taking the visit or the trip which costed only minimum. So that will be the final answer we'll be taking. And so finally, from the leaf node, the person will be reaching to the road number 1, that is the starting location, right? So this is what we can understand from this state space tree. I hope if you remember the previous example which we saw in branch and bound is, we solve 0, 1 knapsack using this branch and bound, right? I hope you remember this. And also one more thing we learn here is, another one technique to solve is backtracking. Actually, what is the difference between backtracking and branch and bound? Already in one zero problem of 0 knapsack. So I hope you know what will be happening in branch and bound. And also we solve 0 knapsack using backtracking also. So you know how the backtracking will be functioning. What is the difference between this both backtracking and branch and bound is, if you remember this backtracking, how does we go is, for example, we will be moving from this root node, and we'll be following, coming down, coming down, coming down. So if anything fail, then we will be backtrack, come back, and we'll be going here. If anything go wrong, again we backtrack, and this is how we will be depth, like coming here, then we'll come here. If something went wrong, again we'll come here, then we'll, so in this backtracking, this is how the traversal will be. So it's like a depth is first, right? To come to the depth and then backtrack. So this is what will be happening in the backtracking. And then out of all this, we will be finding the minimum cost. So if we want to solve a problem using backtracking, we will be getting the minimum cost out of all the solution. We will be getting the minimum cost, so we can use it in optimization. But from this itself, you can understand, if I do this type of problem solving, and if I visit all this node, so what is the problem is, it will consume lot of time. Because why it is going to consume lot of time? Because I have to visit every node, and I'll be going one by here, then backtrack, come here, then backtrack, come here. Finally, the solution will be good. It will be giving us the optimized solution. But what is the problem in backtracking is time consuming. It will be consuming lot of time to solve it. So generally, whenever we have a time constraint problem, we won't choose to go for it, go for backtracking. So what will happen in the branch and bound? In the same type of problem, how will you solve it using branch and bound? If you remember zero knapsack, in what we did is, we will be having an upper bound, and then we won't go by the depth wise. How we solve is, we will be going by level base. So what will we do? From 1, we'll be solving this 2, 3, 4. Then this 2, 3, 4, we will be having who is a minimum, right? We'll be finding who is a minimum, and then from that we will be further expanding the minimum, and further we will be expanding in the level wise only. Again, we'll be finding if who is a minimum. Still, then we will be continuing with the minimum one. Likewise, it will be traversing in level ways, not depth ways. So since we are going to use the level ways, traversal, so the cost taken and the time taken will be reduced, and unnecessary steps can also be avoided. So we don't want to traverse in all the path. Somehow we can reduce the traversal, and we will be consuming very less time. So this is what the difference between backtracking and finding the solution, branching and bounding and finding the solution. So backtracking means it will be happening depth ways, and branch and bound means it will be doing this traversal in level ways by fixing some bounds for the nodes, and unnecessary nodes will be killed based on some condition. So that is how we can solve it. So let us solve this traveling salesman problem with an example. Okay. So let me take a new example here. Okay. So let us take a new example, and we'll be solving it using this branch and bound. First, for that, let me take a graph first. So let us take the graph as 1, 2, 4, and 3, 5. Okay. So this is my graph. Okay, this is my graph. And this graph, let me draw the adjacency matrix also, which help us to understand the cost of traveling between all these nodes. So the adjacency matrix is like this: 3, 4, 5. 2. So when you solve this adjacency matrix, and the graph will be given in the question itself. So the values of that is 20, 30, 10, 11. 15, infinity, 16, 4, 2, 3, 5, infinity 2, 4, and then 19, 6, 18, infinity 3, 16, 4, 7, 16, and infinity. Okay, so this is the adjacency matrix for this particular graph. So how we are going to solve this using branch and boundaries? You know, if you remember zero on knapsack, we will be having an upper bound. That upper bound only will help us to bound the particular node. So, do we want to proceed further or do we want to kill the particular node? That will be decided by seeing the upper bound value. So, here also we want to fix the upper bound. So, in this problem, how we are going to fix the upper bound is, for that what you have to do is, in each row and in each column, what we'll generally will do is we will be finding the minimum value. So first we will go one by one. Each row we have to find who is the minimum value. So in this row, who is the minimum value? Infinity, 20, 30, 10 and 11. So out of all, the minimum value is 10. And then if you see the second row, the minimum value is 2. And in the third row, the minimum value is 2. And in the fourth row, the minimum value is 3. And in the fifth row, the minimum value is 4. Okay. So this is how we will be finding the minimum value in the row base. And if you find the total cost, it is 21 in case of row. Same thing you have to do. So after you find this minimum value, what you have to do is you have to reduce this matrix. Okay, we have to find the reduced matrix, which means actually general objective is we want to reduce it, and somehow in any one of the value you have to bring the costs to 0. So what we have to do is, for example, in all of this, we found the minimum value is 10. In all of this, we found the minimum value is 2. So when we reduce the matrix, what we will be keeping in our mind is any one of this value should become 0. Here also any one of this value should become 0. Here also any one of the values should become 0. So if I want to get it, what shall we do? Generally, you all be good in maths, right? When you solve some equation, if you want to do something, you have to do the same thing for all the values. Same here also, what we are going to do here is, we are going to subtract this 10 from all these values, and in the second row we are going to subtract this 2 from all this value. That is how we will be reducing this matrix. And in the third row, 2 is the minimum, right? So we will be subtracting 2 from all these values. So when we do that, how will we get the matrices? When we subtract 10 from the first row, the result will be infinity, 10, 20, 0 and 1. So I have reduced the first row. Similarly, in the second row, I have to reduce it by subtracting the second row with 2. So I'll be getting the value 13, infinity, 14, and 2 and 0. And similarly in the third row, again in the third row should be subtracted with this 2 value. So I'll be getting the value as 1, which means 3 minus 2 is 1, 5 minus 2 is 3, infinity minus anything you will get infinity only. Then 2 minus 2 is 0, 4 minus 2 is 2. And the fourth row should be subtracted with 3. So when I subtract 3 from it, so what will you get here is 16. Here it is subtracting from 3, so I'll get 3. And here I am subtracting, so I'll get 15. And then here I'll get infinity. And here I get 0. And similarly, the last row should be subtracted with the minimum value of it, that is 14. So we'll be getting the value as 12. Then 0 and 7. Sorry. So when you subtract 4 from 7, you'll get 3. And then here you will get 12. And here you'll get infinity. So this is what the reduced matrix. So now we did we did with row wise, right? Now the same thing you have to reduce it column wise also. Every time we have to reduce it column wise, and also we have to reduce row wise. Now we finished row wise. Now we are going to reduce by column. So what you have to do, so you can rewrite it and you can also do the same with the same matrix. I'm going to do in this matrix itself. So here, again, what is the first step we did when we did with the row? We will be finding the minimum value in each row and then we subtracted it, right? So here also what you are going to do is, we are going to find the minimum value in each of the columns. So the minimum value in this column is 1, the minimum value here is 0, here the minimum value is 3, and here it is 0, and here it is 0. So as we saw, as I told you already, whenever you do the reduction, if we get a 0, any one of the value in this column or any of the column becomes 0, then it's nothing, we don't want to subtract anything out of it, right? Now, if you see here in this full column, we don't have any zero value. And also in this third column also, we don't have any zero value. So what you have to do here, if you subtract all this with zero also, you will get the same value. So again, we have to reduce the matrix using column wise. So when you reduce it, how does this matrix will be changing? So from the column number, so this is column number 1, 2, 3, 4, and 5. And similarly, we know the rows as well. So now we are going to subtract 1 from the column number 1. So when I subtract, how will I get this? We will be getting the again reduced matrix like infinity, 12, 0, because 1 minus 16 minus 1 we will be getting 15, 12 minus 1 we will be getting the answer as 11. And the second column we don't want to do anything because we got the minimum value is 0, 0 minus anything you will get 0 only, so we will be writing as it is. And if you see the third column here, we don't have zero value, which means we got the minimum value as 3, right? So we have to subtract 3 from third column. So we will be getting 17, 11, infinity, 12, and 0. And if you see the fourth column, already the minimum value is 0. So we will be writing the same thing because if you subtract 0 with any one, you will get the same thing. The last fifth column also 0 we have as a minimum value. So you will be getting the same value as it is. So this is our final reduced matrix. Okay, this is our reduced matrix. Now, already when we reduce the row wise, the cost we got is 21, right? And when we reduce by column wise, row wise, the cost we reduced is 21. And when we did by column wise, the cost we reduce is 1 plus 2, which is equal to 4. So the total cost which we reduced is 21 plus 4, which is equal to 25. Okay, so first what we did, this is the adjacency matrix. We have to reduce the matrix. Why we are doing all this thing is, we want to have a bound, right? Always in branch and bound, we'll be fixing a bound. So the upper bound, we want to find the upper bound. So the cost, so how much the cost will be in and around when we travel throughout. So we are finding that by reducing the matrix. So first we have to reduce the column wise, and then first we did by row wise, then we did by column wise. We reduced this, we found the minimum value. Using the minimum value, we subtracted all the values. Here the minimum value is 0, so same thing will be coming. So finally we got this. So now we know the upper bound. Using this cost, we can fix the upper bound. So now to solve this traveling salesman problem using branch and bound, we got the upper bound. That is taken, the cost is taken as the upper bound. So that is 25. So initially our upper bound value is 25. So now what we are going to do next is, we are going to solve using state space tree. So as in backtracking, in branch and bound also we are going to do it by state space tree. So let's start. Now we know the upper bound. Okay. So to do that, from where we have to start it, this is the matrix we have to start with only. So this is the final reduced matrix. So using this only we are going to proceed as well. So as usually we know, whenever we will be starting with reduced state space tree, we will be starting from particular node. So let us say we are going to start from the node number one. This is the row number one. Okay, this one, and this one is just we gave the name for this particular node. Okay, so initially, so in 0 and 1 knapsack problem, if you remember, for each and every node we found two values. We found cost as well as the bound, upper bound value. So here in this branch and bound, we are going to calculate only one value only. So initially when you start, for every node we are going to find the cost. So initially when you start, the cost we have is 25. And in 0 knapsack, we updated this upper bound by seeing the cost value, right? Here, how we are going to, if any one of the, in 0 knapsack, if any one of the upper bound is less than the upper bound which we already have, by that we updated this the upper bound. In this traveling salesman problem using branch and bound, how we are going to update this upper bound is once you reach the leaf node, that leaf node's cost will become the upper bound. In that time only, we will be updating the upper bound. I am repeating. Once you reach the leaf node, that leaf node cost will become the updated upper bound. Okay. So as usual, we have started from the node number 1. So when you start from the node number 1, what are the other possible place we can go for is, we can go to 2, we can go to 3, we can go to 4, or also we can go to 5. So here is a connection. So first we know that branch and bound means it will be proceeding level base, right? So from 1 we can proceed to 2, and we can proceed to 3, proceed to 4, even we can proceed to 5. So then what will we do? So then we will be finding the cost of all this node in this level, in this particular level. We will be finding the cost of 2, 3, 4 and 5, and then out of all which have the minimum cost, with that we will be proceeding. So that is what we will be generally doing in branch and bound. So that is what we are going to do here as well. So to proceed here, every time we have to calculate the cost. So when we calculate this cost, we have to do the same thing. So what is our input for this is this matrix only. So first we are going to see when I travel from 1 to 2, okay, which means 1 to 2, this is 1 to 3, this is 1 to 4, this is 1 to 5. So we are going to check from 1 to 2. When I move from 1 to 2, we have to find the cost. So how we are going to update this matrix is, when I go from 1 to 2, we have to say the row number 1 and the column number 2 should be converted to infinity. Again I say, when I move from 1 to 2 means, this is, we have to say the row number 1 and the column number 2 should be updated with infinity of this matrix as the input. So how does it convert? So we know that in this, who is our, this is our row number 1. 1, 2, 3, 4, 5, and this is 1, 2, 3, 4. 4, 5, right? So who is our row number 1? So this is our row number 1. And who is our column number 1? This is our column number, this is our column number 2. So we have to update this row, this particular row, and this particular column completely as infinity. So how does our our matrix will be changed to infinity? The first full row will become infinity. So 5 nodes, so 5 infinity, and second node will also, second column will also become infinity. So the rest of the thing, and one more thing you have to remember, when I move from node number 1 to 2, we don't backtrack from 2 to 1, right? That also we know. So if I update this node, if I write the nodes of this one, how does it become is, it will be like, so it is 1, 2, 3, 4, 5, and this is row number 1, 2, 3, 4, and 5. So as I said, when I move from node number 1 to 2, first row and the second column is updated as infinity. One more thing you have to remember is when I come from 1 to 2, I will not go from 2 to 1 again, right? So 2 to 1 you have to again make as infinity. Okay, because we are visiting from 1 to 2. So 1 and second column is completely made as infinity, and then we won't move from 2 to 1. So 2 to 1, 2 to 1. So that will also become infinity. The rest of the value you have to write as it is. So it becomes 11 to 0. From this matrix I am writing. Okay, so this becomes 0, and this one infinity 0 2. So infinity 0 2. And the fourth one, this is 15, 12, infinity 0. So 15, 12, infinity 0. And the last row, so that is 11, 0, 12, and infinity. Okay, so this is the updated matrix when I move from the node number 1 to 2. So again, so what is the objective next? I want to find the cost of it, cost of this, right? So now we are finding the cost when I move from 1 to 2. So if you want to find the cost, we know how to do that. So for that, I will write the formula how to find the cost. Okay, so how to find the cost is, okay, let it be. So cost formula is cost is equal to cost of 1 comma 2 plus its root node plus the newly updated node's cost. Okay, cost of moving from 1 to 2 and the cost of the root node plus the newly updated matrix cost. So we will do this, then you will understand. So what we did here is, what we did first, we have to find the, to find the cost of this. What we did first, we reduced it row wise, and then we reduced it column wise, and then we added the both, so we got the cost, right? Same thing you have to do here as well. So if you see here, the minimum cost here is infinity, so we cannot do anything here. Here the minimum cost is 0. Here the minimum cost is 0. Here also the minimum cost is 0. Here also the minimum cost is 0. So for this full row, it is infinity, so leave it. So here it is full of 0. Second row, minimum is 0. Here we got a 0. Here also minimum is 0. In this row also, the minimum value is 0. So in row wise, nothing to be done, because with this 0 you cannot subtract anything, you will get the same answer only. What is the next thing you have to do? Now we have to see column wise. So when you see this column, when you see in this column, so what is the minimum? Here it is 0, here it is infinity, here it is 0, here it is 0, here it is also 0. So there is no change in this matrix, because column wise and in the row wise there is no change to be done. So now let us find the cost. So how to calculate the cost? Cost of moving from 1 comma 2 is cost is equal to cost of moving 1 comma 2 plus its root node plus the newly updated cost value, which is equal to, what is the cost of moving from 1 to 2? You have to see this. Okay, so cost of moving from this matrix. So to arrive this matrix, who was the parent, or its previous matrix is this matrix, right? So we have to look at this matrix. So what is the first thing? Cost of moving from 1 to 2. So already in this adjacent matrix we have the cost. So cost of moving from 1 to 2 is 10. So we have to say 10 plus, what is the cost of this one's root node? The cost of this one's root node is 25. So we'll be making 25 plus, what is the cost of this present adjacency matrix? We didn't do anything, right? We didn't do any reduction. So it is 0. So the cost is 35. So now we found that the cost of this particular node is 35, right? Similarly, we have to find for the cost of moving from 1 to 3, cost of moving from 1 to 4, cost of moving from 1 to 5, all these things. So as usual, we have to find all this nodes cost, then only we can find who is the minimum, right? So what will you do again? So now again we have to find from 1 to now we want to find the cost of moving from 1 to 3. So earlier we found from moving from 1 to 2. Now we similarly we have to find for 1 to 3. So this matrix will be updated, right? So what shall I do? One second, I'll copy this and paste it there so that you can also view it. So this is what the parent matrix, because from this matrix only we found this. Again, it is a new thing moving from 1 to 3, right? So for that also, when you to calculate from 1 to 3 also, we have to use the same matrix one. So this time what we are going to do is we have to move from 0 to 3. So So if I want to move from 0 to 3, which one will you make it infinity? So as usual, how we did here, the first row and the second column completely made us infinity. So in this case here, what will you do? The first row and the third column should be made infinity, right? So how does our matrix will be converted? So this first row completely will be changed to infinity, infinity, and then here we are going to third. So third column will also be converted to infinity, and then also what is the third thing we did? We cannot move from 3 to 1, right? So 3 to 1 also should be converted to infinity. So 3 to 1 means, so we will make as a matrix. So this is our matrix. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. So now what we said is we cannot move from 3 to 1 again. Okay, because everything will be visited once. So this will also become infinite. So the rest of the value you have to write as it is. So if I write the rest of the value, it becomes 12, infinity, 2, 0, and then here it is 3, infinity, 0, 2. The rest of the values as in the parent matrix we have to write as it is. Okay, 11, 0, 12, and infinity. So we found this matrix. Now again we have to, what is the objective actually? We want to find the cost, right? So if you want to find the cost from moving to 1 to 3, so we will be reducing the matrix. So we know how to reduce it. So first we will be reducing in the row wise. So here this row is full of infinity, leave it. Second row we have the minimum value is 0. Third row also we have 0. Fourth row also we have 0. Fifth row also we have 0. So row wise there is no reduction. Now let us do with column wise. So when you do with column wise, now we have to reduce by this column wise. Okay, so when you reduce by this column, who have the minimum value is this 11. 11 is the minimum value. Here it is 0. Here it's fully infinity. Leave it. Here the minimum value is 0. Here also the minimum value is 0. So what is the next thing? So row wise it is completely 0. Column wise here we got 11, right? So we have to reduce it. So to make it 0, any one of the nodes. So to reduce it, what will you do? We will be subtracting the complete column with this value 11, which means with the minimum value. So how does this matrix will be converted to? It will be like, I'll write it small. So if I completely, I have to subtract this full column with this 11. So it becomes like infinity. And then 12 minus 11 is, you will get as 1. Then infinity. 15 minus 11 you will be getting as 4. 11 minus 11 you will get as 0. Okay. So okay, infinity 1, infinity 4, 0. So then this column we got minimum 0, no problem. Here it is completely infinity, it is 0, so nothing to subtract with the rest. So here we got the answer. The rest of the things you have to write as it is. So infinity, infinity, 2, 0, 3, infinity, 0, 2, 3, infinity, infinity, 0, 0, infinity, 12, infinity, right? So this is our reduced matrix. So we done with it, the reduced matrix, when we move from 1 to 3. So when you do the reduced matrix, what is the next step? We want to find the cost. So we know how to find the cost. So when we find the cost for this, how we calculated the cost of moving from 1 to 2 plus its root node plus the currently updated cost, right? So you can also write the formula of updating this. So how will you calculate the cost of moving from 1 to 3 plus cost of its parent node plus the currently updated matrix cost. So how will we do for this? So cost of moving from 1 comma 3 plus the its root node plus the current node's updated value, which is so here cost of moving from 1 to 3, 1 to, so 17 plus its root node cost, we already know what is the cost of its root node, it is 25. It is 25 plus what is the cost we reduced presently. Row wise we didn't reduce anything, but in column wise we reduced 11 from all the values of the particular column. So the reduced cost of this time is 11. So when we add all this thing, we will be getting the answer as 53. Okay, so now we got the cost of moving from 1 to 3 is 53. So here we can write the cost is equal to 53. Okay, similarly, in the same way, we have to do for cost of 4 and also cost of 5. So how will you do? Again, take the same matrix. So what will you do? The row number 1 and column number 4 will be completely made to infinity, and then from 4 to 1 also will be made infinity. And then after that, what will you do? After doing this, we will be reducing the matrix. First we will be doing row wise, then we will be doing column wise, and then using the same formula, which means cost of 1 comma 4 to its root node cost plus currently updated matrix cost, you will get the cost of this. Similarly with this, okay, so we have to in this way we have to find the cost of it. After finding the cost, out of all this who have the minimum cost, we have to proceed from that. We won't proceed in all the ways. We will be proceeding level wise and who have the minimum cost. And then based upon the upper value, we will be killing the node which crosses upper bound. Okay, so that you have to proceed it. The rest we will be seeing in the next class.